When discussing effective annual rates, we drew the table below. So to recall, this is the value of $100 after 1 year, compounding at an APR of 20%. We found that the value of ST increases as the number of compounding periods increase, but we also found that that difference shrinks as t grows. So a natural question is, what happens if t becomes infinite? Does the value of ST approach a finite number? Well, we know the formula for the future value when we compound using annual percentage rates. Remember, here P is the principal, R is the interest, N is the number of years that have passed, and T is the compounding frequency. So to let T become arbitrarily large, we write this as a limit. Now, we don't know what this means yet, so you'll have to put some faith in what I've written. We also don't know how to evaluate it, but it turns out that the answer involves the natural exponential. This is the future value of continuously compounding interest. Now, a couple things to note. Solving this equation for P will immediately yield the present value formula. If we divide by e to the power of Rn, we get this guy. But just like with the discrete value, let's write this using a negative exponent, so that once again, future and present values are given by the same formula with only a sign change in the exponential. The next note is that R must be stated in terms of an annual percentage rate. We are compounding at every instant in time, so it doesn't make sense to talk about a term rate. So why do all of this work? What are the advantages? Well, first off, there are fewer variables involved with continuous compounding interest. And to see what I mean, let's make a table. So in the future value formula, the variables are only P, R, N, and T, whereas in the continuous case, there simply is no T variable. So we go from having 4 variables to having 3 variables. The next advantage is that it's easier to solve for these variables. If you try and solve the discrete equation for t, it's not possible without the assistance of a computer. The equation is said to be transcendental in t. In the continuous case, there simply is no value of t for which to solve. Where continuously compounding interest really stands out is the n and r variables. Take a moment and see if you can solve for the discrete and continuous equations for n and t. If you've done that, you should have found that r is as follows. It's a nasty equation involving the nth root of an expression, whereas the continuous equation is much more straightforward, as we can see. Solving for n requires employing a completely different technique than the one we used above, while the continuous equation gives a nearly identical answer to r. Thus, continuous compounding interest provides an easier mathematical framework for computing things. Now, what are the disadvantages? Well, continuous compounding interest does not model real life. Nothing grows and compounds at every instant of time. However, this isn't a big problem. The answers you find using continuous compounding interest are similar to those of the discrete case. The differences are very small. And if you're clever about how you write the discrete equation, you can write it in terms of the continuous equation as so. So here, r hat is the value of the thing in the square brackets. And it tells us that continuously compounding at this rate r hat will return the exact same value as compounding discretely with the rate r. And so this leads us to the following definition. Given an APR of r% compounding t times per year, the effective continuous rate is the rate r hat such that a principal compounding continuously at r hat returns the same as the one compounding discretely at the rate r after 1 year. Think about this for a second. This is the same concept as the effective annual rate, but instead of compounding once, we're compounding continuously. Now, according to our previous computation, r hat is t ln 1 plus rt. But this might not satisfy you, since this isn't how we computed the effective annual rate. So let's verify this result in a slightly different way. Let's compute the future value of a principal p after 1 year compounding discretely. We're going to set that equal to the same principal p after 1 year of continuous compounding interest. Since p is not 0, we can remove it from both sides, and in which case solving for t gives exactly the same answer as above. All right, let's do an example with continuous compounding interest. We'll repeat the example we did in the bonds video, but I'll write it out again to remind you of the details. We have a $100 bond with a maturity of 1 year paying $5 coupons. quarterly. What is the present value assuming an APR of 1.5% compounding continuously? All right, let's redraw our timeline from the bonds video. We have a $105 payment in the 12th month and $5 coupons in the quarters in between. The face value's present value is as follows. Here we've pulled back by just 1 year. Now let's set the stage for the rest of the coupons. Coupon 4 also needs to be brought back a year, giving us this. Now take a moment for yourself and see if you can work out the formulas for the present values of the other coupons. Having done that, we can write out the present value of the third coupon. Notice the 3/4 in the exponent. This is because 9 months is 3/4 of a year, and continuously compounding interest is always computed in terms of the total number of years. We can work that out to get 494. Now coupon 2 is the same, but 6 months is equal to half a year. And coupon number 1 has this 1/4 factor owing to the fact that 3 months have passed. The total present value is the sum of all of these numbers. And if you work out what that is, you get 118.32. Okay, so if you go back and you check our numbers from the bonds video, you'll see that these are exactly the same answers as we got in the discrete case. Now, in truth, the answers are different, but the difference is just so small that we don't see it because we rounded to 2 decimal places. So this tells us that continuous compounding interest is a very useful tool. It creates this mathematical framework which is very easy in which to do computations and doesn't give answers that are significantly different from discrete compounding scenarios.